in this section we make the notion of transforms, and especially a software library for managing transforms, a little bit more concrete. We're going to talk about TF, which is the ROS library and framework for handling transforms. So in ROS, the library for transforms is TF, and in particular right now it's at its second generation. So it's TF2 that we're going to be using. You will be reading most about TF2 from its own wiki page, but before we get to that, just to give you a very quick high-level idea of what TF2 and TF in general does for you in ROS. What TF does is it manages a tree of transforms for you. So remember how in the past we've talked about how various frames are relative to each other, how maybe you will have frame A, then relative to frame A you might have frame B, and you have this transform here. Relative to frame B you might have frame C and frame D, and you have these transforms given, and so on and so forth. What TF does for you is it takes care of such a transform tree. So for example, it knows that transform A is your base transform, that B is defined relative to A, that C and D are defined relative to B. So what your job is to tell TF all these individual transforms. So for example, the transform from A to B, or the transform from B to D, or the transform from B to C. And then TF will build this tree for you behind the scenes, and such a tree in general can be way big, especially when dealing with real robotic systems. And at any point you can ask TF, hey, what's the transform, for example, from E to A? Or from A to E? And then TF behind the scenes maintains this tree, so whenever you ask for any transforms that connects two frames in your tree, it'll compute and give you the result. So let's look at a small concrete example. Before we start looking at code, very briefly, this is the TF documentation page. It's on the ROS wiki, and before you start off on assignments, it's important to go through the tutorials here and get a really good sense for how TF works and what TF does. So here we're going to be running some code that uses TF. Let's take a quick look at our code. It's Python ROS code. So first we import ROSPy, we import NumPy, which we're going to use for, which is used for multiplication, matrix multiplications and things like that. We're going to need TF, TF2 ROS, and geometry messages. Okay, so those are our imports. The core of what we do here in the main is we set up a transform broadcaster. What this is, you will know after reading the TF tutorials. And then we always use this broadcaster to keep broadcasting specific transforms to the rest of the ROS universe. So until we're shut down via Control-C, every half a second we are going to publish some transforms to the world. What transforms are we publishing? This is the publish transform function. This is really the most interesting bit. This is very typical for transform libraries, software transform libraries. Here we're using one of them, many others will do the same. So here we are setting up one specific transform based on a translation component and a rotation component. So let's look at it inside out, right? So first, we say we have our rotation expressed as Euler angles. 1, 1, 1 as Euler angles, okay? First, what we are doing here is we are converting that into a quaternion. Again, you don't have to know by heart how to convert from Euler angles to quaternions. Libraries will do that for you. The TF transformations library will do that for you. So then we have our quaternion. Then we are going from a quaternion to a rotation matrix. So this function takes in a quaternion and gives us the rotation matrix. So overall, this bit here, from here until here, sets up a rotation matrix from a quaternion from a set of Euler angles. This is very typical for the kind of transforms that you'll find yourselves doing whenever dealing with software libraries. Then you have the translation bit, which is just very simply 3 numbers, tx, ty, tz. This sets up a matrix, a transform matrix just for the translation. And then this bit all the way from here to here concatenates our translation and our rotation. So this gives us one big transform matrix, right? So when we're done with all of that, T1 is a transform matrix. The translation component is 1, 1, 1. The rotation component is a matrix that's created from a quaternion that's created from Euler angles 1, 1, and 1. And then we have a little bit of code here that allows us to tell the ROS universe, hey, who is this transform between? And we are telling it that this is a transform from the frame world, which we, by convention here, decide is our base coordinate frame, to frame F1. So T1 is the transform from the world coordinate frame into coordinate frame F1. Then we're going to do the same thing again with a different transform. We're going to set up T2. This time the rotation bit is axis angle, right? So we have a rotation by 90 degrees around the x-axis. So from the axis angle representation, we go to a quaternion using the library. Then from a quaternion, we go to a rotation matrix. Then we concatenate that with the translation bit, which is 1, 0, 0, so translation along x and nothing along x and y, along y and z, sorry. And we get T2, our second transform matrix. And then we tell the world, hey, this is a transform from frame F1 into frame F2. And then we use the broadcaster to publish these transforms. So let's run this code and see what happens. So first we're going to need a ROS core. Then I'm going to start RViz, our visualizer, so that we can see the results of what we're doing. And then finally, so far we have nothing in RViz. And then I'm going to start our little transform broadcaster code. Right, so ROS run tf2 examples, tf2 examples.py. Now this is broadcasting its transforms. So if we go back to RViz, now all of a sudden the frames have shown up, and we can check the relative positioning of these frames, right? So the convention, whenever we see frames in RViz, you have 3 axes, a red one, a green one, and the blue one. Unfortunately, the green one doesn't show up in these recorded lectures. This is a technical difficulty. But when you run RViz on your computers, you're going to see the red axis, the green axis, and the blue axis for every coordinate frame. And the convention that you have to remember is that red is x, green is y, and blue is z, right? So in general, you can think RGB, so red, green, and blue. Red is x, green is y, but this one we're not seeing it here. You'll see it on your computers, and blue is z, okay? So here we have our world coordinate frame. You see here the x and the z axes, and relative to it we have our frame F1, okay? What's the transform between the world and F1? Again, it's this, right? So it's a translation along x and along y, and a rotation by Euler angles 1, 1, 1. What exactly is that rotation? Well, this, right, you see that the x and z axis in F1 are rotated relative to the x and z axis of the world. And then the translation is, as you can see, along the x and the y axis. We have no translation component between F1 and world. We have no translation component along z, right? We only have a translation along x and y. And then let's look at the transform between F1 and F2. The transform between F1 and F2 is a little simpler. So we're going to have a rotation by 90 degrees around x, and a translation that's purely along x. So then if we go back to our viz, you can see that the translation from F1 to F2 is purely along the x-axis of F1, and that the rotation from F1 to F2 is a rotation by 90 degrees around the x-axis. You can see that the x-axis between F1 and F2 is the same, right? And then the other axes have rotated by 90 degrees. So now we have published those two transforms, so now the ROS ecosystem knows about both of them. Let's do a couple of more things. Let's bring in this little bit of the code. Okay, what's happening here? One nice thing about these transform libraries is it's very easy to do things like invert transforms, right? So we already have T2 defined. So T2 is defined here. Now we're just going to say, hey, T2 inverse is just the inverse of it. Piece of cake, right? So then we're going to tell it there is a transform F3 which is relative to F2, and the transform from F2 to F3 is T2 inverse, right? So to go from F1 to F2, we've used T2, then from F2 to F3, we use T2 inverse. Where do you think F3 is going to end up? Well, we run this, and not surprisingly, F3 ends up directly above F1, right? You can see here that F3 and F1 are actually superimposed on each other. And that makes a lot of sense, right? We've gone from F1, frame 1, to frame 2 using transform 2. Then from frame 2, if we're going to do transform 2 inverse, we're going to end up back at F1. So F1 and F3 are actually one and the same, as you can see here. And then we're going to do the same thing one more time. Let's go back to the code and comment in this bit. Okay, and we're going to say that from F3, we're going to go to F4 by applying the inverse of transform 1. So then once we run that bit, not surprisingly, F4 ends up right on top of our original coordinate system, which is the world. You can see that they are exactly superimposed here. So overall, our transform chain is we go from the world to F1 using T1, then we go to F2 using T2. T2 inverse brings us back here, and then T1 inverse brings us back to the world. So the 4 transforms that we are chaining in this piece of code, from the world to F1 times the transform from F1 to F2 times the transform from F2 to F3 times the transform from F3 to F4. But in fact, right, we've defined these as T1 times T2 times T2 to the -1 times T1 to the -1. So these cancel out, then these cancel out, and we get the identity, which means that F4 is exactly on top of our starting coordinate system, the world, which is the way we've defined it. One last note, the transforms.py library is available online on GitHub. So a lot of the conversions that we've used here come from this particular file, which is well documented, and you can see here the kinds of operations that you can perform. In general, what you want to remember here is that these kinds of conversions, from quaternions to Euler angles to matrices to transform, multiplications, chaining, taking inverses, you will end up in practice using a software library for all of these, and it's a good idea to get very familiar with your software library for transforms, know how to use it, know how to chain, know how to multiply, know how to do those conversions. The theory you now know, the math behind it often is done by the library for you, and then it's just a matter of being organized and keeping track of your origin, keeping track of your coordinate frame, and always knowing which frame you're operating in.